Hello, and welcome back to the course on Physics for Engineers. So we are still on chapter 12 of the course and for the second lesson of the course. So before we proceed with the second lesson, let us first review some concepts. So in the previous lesson, we have defined electric current, resistance, and EMF. And also we have defined the relationship between these three, which is given by Ohm's law. With EMF being a source of, or being the EMF being somewhat equivalent to the voltage. So for this lesson, we will be talking about resistors and their connections. So basically, these are devices with resistance. So a resistor is an electrical device with a specific or variable resistance. So this is one of the elements of a circuit. So we have presented before that in order to make the very simplest circuit, you just need a battery and a device with resistance, and then of course some connecting wires. So a resistor is one of the elements of a circuit. So you may have encountered different types of resistance. So resistors, I mean. So if you have resistors like this, these resistors have a fixed resistance depending on their colors. There also we also have variable resistances. So basically, the knobs that you have in your speakers or to control the brightness of your lights or lamps, those are basically variable resistors, usually called varistors. So variable resistors. So the circuit symbol for resistance is a zigzag line. So this is the circuit symbol for a resistor. It's a zigzag line. So it represents basically the hardships of a moving charge or current when it flows through a material with resistance. So when a current flows through a material with resistance, then it will actually be going in a zigzag, sometimes something like in a zigzag manner, because it will not go straight. It will have some resistance. It will the resistance will basically resist the flow of current. So that one. So if your resistance is similar to the resistor that I have shown you earlier, where there are different colored bands, then you can determine the resistance of that resistor by just looking at the colors of the band. So the resistance is basically the first band represents the first digit of the resistance. The second band is the second digit. The third band is the multiplier, and the last band represents the tolerance. So the resistance is basically the first digit, second digit multiplied by the third digit or third band, the multiplier, plus and minus the tolerance. So these are the color coding for the resistors. So black is 0, brown is 1, red is 2, orange is 3. So that's the colors of the rainbow basically. Black, brown, then RGB. Up to, and then but you have gray 8 and white 9. So if as a multiplier, so this is as a digit no, for the first and second band. For the third band, so if it's black, then 10 to the 0 or 1. If it's brown, then it's 10 to the 1 or 10, and so on. So if it's white, its value as a digit is 9. And its value as a multiplier, if it's in the third band, it's 10 to the 9. So that's 10 to the 9 is giga, the giga prefix. 10 to the 6 is mega. 10 to the 3 is kilo. So kilo ohms, mega ohms, giga ohms. So for the tolerance, if there's no fourth band, then that's a plus and minus 20% tolerance. Silver is plus and minus 10%, and gold is plus and minus 5%. So the tolerance gives you how much the value of the resistance will change. So for example, in this case, our first digit, our first band is green. So green is 5. So the first digit is 5. And then the second band is violet. And then, so you have 7. So 7 times the multiplier is, the third band is red. So red is 10 squared, or 10 to the 2, or times 100. 10 squared is 100. So that is the resistance basically. Then plus and minus 5% of that value, because our final band is gold. So 5%. So meaning, so this is 57 times 100, that is 57,000 or 5,000, sorry, 5,700 ohms, plus and minus 5% of 5,700, which is 285 ohms. This means that this resistor can have values from 5,700 minus 285, that is 5,415 ohms, up to 5,700 plus 285, and that is 5,985 ohms. So the tolerance tells you how much the specific resistance can slightly vary. So if you want a more accurate resistor, you should choose the one with the smallest tolerance, such as gold, since gold only has plus and minus 5%. If there's no tolerance, there's no fourth band, then that will have a tolerance of plus and minus 20%. So the values may vary very wildly. So for example, if you have this resistor and you measure it using a device, a multimeter or an ohm meter. An ohm meter is a device for measuring resistance. Then it can have values from 5,415 ohms to 5,985 ohms. Okay, so there are two basic types of resistor connection. The first one is the series connection. So only one end of a resistor is connected to the other. So this is one resistor, this is another resistor. And you connect one end of the first resistor to the second end of the other resistor. So the equivalent resistance is actually larger if you have a series connection of resistors. So in the previous chapter on electrostatics, you have discussed about series and parallel connections of capacitors. And their relationship is actually reverse. So in capacitors connected in series, the equivalent capacitance is actually smaller, but in resistors, the equivalent resistance is larger. So the equivalent resistance is basically just the addition of all the resistors in series. So R1, R2 plus R3 plus R4 and so on, depending on how many resistors are connected in series. Then you have the parallel connection, wherein both ends of the resistors are connected to one another. So the end of resistor 1, which is this one, both ends, is connected to both ends of resistor 2. So that is the parallel connection. So the equivalent resistance is smaller. Again, in contrast or in opposite to capacitors connected in parallel. So capacitors connected in parallel, the equivalent capacitance is actually larger. So opposite. So the formulas for the resistor, for the capacitor connections and the resistor connections are actually inverse of each other. So the equivalent resistance for resistors connected in parallel is this one. So 1 over R1 plus 1 over R2, and then after you add all of the inverse resistance, you take the inverse, or raised to the power of negative 1. So that one. So what's the purpose of why connect resistors in series and in parallel? So maybe you want to create a larger or smaller resistance, but you only have limited resistances or resistors. So suppose you only have a 1 ohm resistor and another 1 ohm resistor, but you want to have a 2 ohm resistor, so you just connect them in series. And say you want 1/2 ohm resistor, and you only have again a 1 ohm resistor and another 1 ohm resistor, so you connect them in parallel so that the equivalent resistance is now 1/2 ohms. So that, okay. So series connection similar to capacitors. In capacitors, series connection has same charge. So in resistors, it's same current, but the voltage is divided. So all series connections are voltage dividers. So the voltage will now be distributed to R1 and R2. So the current is the same, but the voltage is divided between resistor 1, resistor 2, resistor 3, and so on, depending on how many resistors are connected in series. Parallel connection, same voltage. Similar with capacitor, parallel connection, it will have the same voltage, but the current is divided. In the same manner that as in capacitors, charge is divided in parallel connection. So similarly, current is divided in parallel connection. So same voltage. So V1, the voltage of resistor 1 here and resistor 2 are the same because they are connected in parallel, but their current is divided. So current now will now be divided between R1 and R2. That is it. So let's now have an example. So we have this network of resistors. So you have 5 resistors, R1, R2, R3 until R5, and these are their given values. So R1, this one is 1 ohm, R2 is also 1 ohm, R3 is also it's 2 ohms, R4, this one is 1 ohm, and R5 is 2 ohms. So find the equivalent resistance of this network. So it is just basically the same as how you simplify capacitors. So find the basic connections first, the basic series and parallel connections, and then combine them into an equivalent resistor. So this is how we will analyze the problem. So R1 and R2 are obviously in series, so we can basically merge them to an equivalent resistor R12. And then R12 and R3 are obviously parallel connection because you connect both of their ends. So that's parallel connection. So you can merge these two as an equivalent resistor R12 and R3 or R123. And then lastly, these 3 resistors left are all in series, so I can merge them into an equivalent resistance R1, 2, 3, 4, 5, or basically R equivalents, the final equivalent resistance. So first, let's solve for R12. So R12 is series connection, basically just R1 plus R2. You add just the 2 resistances. So 1 ohm plus 1 ohm, you get 2 ohms. So R12 is 2 ohms. And then we solve for R123, the parallel connection between R12 and R3. So you will get from the formula R123 is just 1 over R12, the first resistor, plus 1 over R3, the second resistor. And then take the inverse. So you have 1/2 plus 1/2. So you will have 1 over 1 ohm. And you take the inverse of that, 1 over 1 ohm is 1 ohm. So that's R123. So lastly, you now have a series connection. So just add the 3 resistances. So you just have R123 plus R4 plus R5. And then R123 is now 1 ohm. R4 is 1 ohm. R5 is 2 ohms. So 1 plus 1 plus 2, you get R equivalence, the equivalent resistance of this network as 4 ohms. So just the same manner as how we solve capacitor connections. So that is the end of this lesson. Basically, since we only focus on resistors and their connections. So I will see you again in the next lesson for chapter 12, DC circuits. So bye bye.